Good morning. It is my pleasure to introduce you to Ada Vernet Crua. I'm sorry for this small delay due to some technical issues. It seems that we have some problems connecting with the United States. So I'm gonna be showing Ada's presentation from my computer, and she will be talking, of course. So let me put into context this PhD. Our collaboration with Northeastern University started in the summer of 2017. I went there with a Fulbright scholarship to improve the antibacterial coatings that we were developing here at the Institute of Micro and Nanotechnology in Madrid. And I work with this student in principle, with David Medina, and this university, Universitat Rovira i Virgili, here in Spain, in Tarragona, has an agreement with Northeastern University for their master thesis. So the master thesis of Universitat Rovira i Virgili can be done at Northeastern University, and when the students are brilliant, they usually offer them to continue with a PhD. This is what happened with David, and as we were working together efficiently, I became his supervisor, co-supervisor, of course. So we were doing this. We were studying these antibacterial coatings made of titanium nanocolumns that you can see on violet here. You can see these two black dots are two Staphylococcus aureus. And you can see these yellow bars, and these yellow bars are tellurium nanorods. And with the titanium coating, we were decreasing the addition of bacteria, and with the tellurium nanorods, we were killing them. The tellurium nanorods were prepared at Northeastern University with a hydrothermal method. And you can see on the right that it also works with gram-negative bacteria. This is bacteria proliferation. For different samples, the initial implant is the flat one. You can see that with the titanium nanocolumn, we decrease the addition of bacteria and the proliferation of bacteria to 1/2. And we can even decrease that using the tellurium nanorods, because the tellurium nanorods are going to kill bacteria. So that was in David Medina's PhD thesis that was successfully presented in December 2020. And then now I will show you what Ada has been doing as a continuation of that work. Ada was also a master's student from Rovira i Virgili, and she was brilliant, and she has done her PhD at Northeastern University. She started in 2018, and her idea was to prepare these tellurium nanostructures using green synthesis. And in her case, the nanostructures are going to be alone. They don't need to have a template to grow, and they can be used not only for implants but for other devices. Ada, besides several publications, she received a Best Presentation Award at the IAAS meeting in 2019, and she has co-founded a company, Cell Biotechnology, and she has 4 patent applications. And Ada has successfully presented her PhD thesis last month. And just to finish, I would like to show you this picture that we took in Rhodes, where we met for a conference. You can see here these 2 students, David and Ada. We have 6 joint papers with them. Here you can see Dr. Daniel Arcos from Complutense University. We have started to study these antibacterial coatings with him, and we have 2 joint papers. And this is Jorge Cholula from Tech Monterrey. He has been performing some characterization of the nanostructures. We have 5 joint papers with him and with Northeastern University. And also we have an iLink project funded by the SIC and Tech Monterrey together, and we have additionally another 2 papers with him within this framework of the iLink project. So that's all regarding my presentation of the context of Ada's PhD. And now we will start with Ada's presentation. So Ada, please, you can start whenever you want.
Well, thanks for this kind introduction, and thank you everyone for being here today. I'm really sorry for this delay. So it's my pleasure to talk about the work I carried during these past 4 years at Northeastern in collaboration with Instituto de Micro y Nanotecnología. So without further ado, let's start the presentation. So I wanted to start this project and this presentation talking a little bit about the background behind my project. So we will start talking about the leading concerns in the healthcare system nowadays. Next. So the first problem we will be talking today is antimicrobial resistance, also known as AMR, which is basically the ability that some microorganisms like bacteria have developed against the drugs that once could kill them. And that basically means that common antibiotics are no longer a solution to treat these resistant stains, and therefore they are triggering a global scale crisis. So AMR is in fact not a novel concept. It happens as a result of natural adaptation to the environment, as naturally bacteria adapt, change, and mutate. However, factors such as the misuse and overuse of antibiotics have made this problem bigger and bigger. Next. So besides AMR, there's another worrying concern in healthcare, and this is cancer. So cancer is the group of diseases that's based on the abnormal growth of cells that basically can form tumors, which can spread into other tissues and cause death. So cancer represents the second leading cause of death in the US, but also in Spain. It causes approximately over 500,000 deaths in the US, which is roughly 100,000 deaths in Spain. And only by 2022, more than 2 million new diagnoses will be done in the United States, approximately 300,000 in Spain. So similar than what happens with antimicrobial resistance too, some cancer cells can become resistant to several treatments, and especially to chemotherapy ones, and they make this problem even bigger and more complicated. Next. So you might be wondering, why am I talking about such different concerns in the healthcare system? Well, unfortunately, AMR and cancer can occur at the same time. And this is because cancer patients have weakened immune systems, and that limits basically the ability to fight infections. So this is as common as 33% of cancer patients needing antibiotics at some point of their treatment. And these statistics are even more concerning in some tissues, for example, the skin. So in those terms, we will be talking about skin cancer, and which is in fact the most common type of cancer in the US. It's not as common in Spain, but still problematic. And we will be focusing on melanoma. So melanoma, if we take a look at this image here on the left, is basically the cancer that happens on the melanocytes, which are these tiny little cells in the epidermis. And although it's not the most common type of a skin cancer, it is the deadliest and has high index of drug resistance, recurrence, and metastasis. On the other hand, in terms of infections, we will be talking about skin and soft tissue infections, which are basically the group of diseases that occur on the skin and its supporting tissues. And because we'll be talking about melanoma, we inevitably have to talk about surgical site infections, which are basically the infections that happen where a surgery took place. And this is because the most common treatment for melanoma is surgery. So all these kind of infections are also the most common side effect of any kind of cancer, in fact. And this is because the skin is the first layer of defense to external organisms. So basically, any cut, any wound will expose the skin to these bacteria. And there are many, many different types of bacteria that can cause these infections. However, Staphylococcus aureus is a gram-positive bacteria, and Escherichia coli as a gram-negative bacteria are some of the most common. And in fact, these two bacteria are also highly resistant to antibiotics. So it is clear that we need to find a solution that has antimicrobial and anti-cancer properties, and that could basically be used simultaneous in simultaneous technologies to be used, for example, in skin patch application. Next. And how are we going to do this exactly? And that's by using nanotechnology. So I'm pretty sure all of you are familiar with nanotechnology. But let me summarize why exactly did we choose this approach and how we did it. So there are many, many types of nanomaterials with different compositions, sizes, morphologies. But what makes them so unique, and that's why we want to use them, is because they are so small that basically there's a really good interaction between nanomaterials and living organisms like human cells or bacteria. And they're also highly tunable and are highly reactive. So we want to use this nanomaterial, but how are we going to synthesize it? So because we not only care about health, but also the environment, we will try to synthesize these materials following less hazardous routes of synthesis, which are also known as green synthesis or eco-friendly synthesis. And what material will we be synthesizing? Well, again, there are multiple types of materials that basically have been employed in literature for both anti-cancer and antibacterial activities. For example, copper, noble metals like gold or silver, or magnetic nanoparticles. And they all have their advantages and their limitations. For example, some of these have already started to show some resistance to bacteria. So basically, it's really clear that we have to find something that works in a different way. And that's where we came up with tellurium. So tellurium is a rare metalloid, and it's highly used in the semiconductor industry, but it's unknown, its biomedical properties are highly unknown. So that's where our research opportunity comes. Next. So that's basically what they decided to do. So we will use this tellurium to synthesize nanomaterials that basically have anti-cancer and antibacterial properties, and we will target the skin. And for that, what we did is divide this research into main sections. So the first one is the synthesis of tellurium nanowires, and we will use two different routes of synthesis, a traditional physical-chemical approach, and also a less hazardous process. And we will investigate basically the differences between both of these materials, and therefore, if it's possible to use tellurium as biomedical agent for applications in the skin. And then in the second section, we will synthesize a tellurium nanocomposite. So a nanocomposite is basically the union of two nanomaterials, in this case, a nanowire, a tellurium nanowire, and a metallic nanoparticle. And this is because we want to take advantage of the unique structure of these green tellurium nanowires, but also because we believe that basically two nanomaterials will work better than one. And then we will basically investigate the biomedical properties of these two different materials. We will compare it with the bare nanowire, and finally try to understand the mechanism of action of these nanocomposites and try to better engineer them. Next slide, please. So let's just start this first part, the synthesis of the tellurium nanowires. And basically wanted to say that this work is related to a published article and also a patent. So this is basically how we did it. We synthesized two different nanowires, again, using a traditional physical-chemical approach, which is marked here as chemical synthesis, and a less hazardous route of synthesis, which is here at the bottom, and that for the ease of the talk, we call it green. but it's only less hazardous. So in both cases, we have used what is called an hydrothermal synthesis, which is basically a reaction that happens at high temperature and high pressure. And the differences in between these two processes are basically the reagents that we use. So for the chemical synthesis here at the top, we use a tellurium salt, and then we use hydrazine and ammonia, which are basically reducing agents, and then PVP, which is a polymer, as acting as a caping agent. And in that way, we obtain the chemical tellurium nanowires. But for the green synthesis route, what we did is using, again, a tellurium salt, but we mixed it with starch, which is basically a polymer, a natural polymer coming from potatoes, and then we obtain these green tellurium nanowires. Next. So here we have an image on how these materials look like. So here at the top, we have the chemical tellurium nanowires, and at the bottom, we have the green tellurium nanowires. So if we take a look, just looking at them, you already see that there are some differences. And for example, the chemical tellurium nanowires on the top show irregular structures, and they can also form clusters. They have different sizes, different shapes, which are approximately 30 nanometers in width. And we believe that these irregularities would basically be shown up in the biomedical properties that we will see later, and will probably cause some issues. On the other hand, the green tellurium nanowires at the bottom show a homogeneous star-shaped structure, which is approximately 20 nanometers in width and basically repeats over time. Next. So we have extensively characterized these structures, but I'm just going to show some of them here to basically summarize the most important findings. So here at the lab, we have the infrared analysis. On the right, we have the X-ray for electron spectroscopy. So what these techniques, along others, show us is that basically both green and chemical tellurium nanowires contain metallic tellurium, as well as tellurium oxide. And this is especially seen on the green tellurium nanostructure. On the infrared analysis, we can see these bonds, but also we can see other bonds that are commonly present in potato starch. And what this is suggesting basically is that the starch has been incorporated in the structure in form of a coating. Other important facts, for example, is that we can detect some non-reactive materials like nitrogen in the chemical tellurium nanowires. And this, for example, is seen on the XPS analysis. But basically, the main conclusion we see here and in other experiments is that the green tellurium nanowire structure presents a coating of starch along the wire structure. Well, this is not seen for the chemical ones, which is basically uncoated. Next. So after doing characterization, we started testing biomedical properties of these materials, and we did test several concentrations going from 5 to 100 micrograms per ml. And the first property we tested was cytocompatibility. And for that, what we did is what's called an MTS assay. So for this test and the rest of tests that I will be showing today that involve human cells, we basically use two different kinds of cells. The first one being HDF, or human dermal fibroblasts, which is basically healthy skin, and the other one being melanoma cells, which are the cancerous ones that we are interested in. So as I was saying, this is an MTS assay, and what this does is basically quantify metabolism in the metabolic activity in cells. So generally, a low metabolic activity is associated with a decrease in cell proliferation or cell concentration, and that therefore it's associated with cell death. So the first thing I wanted to mention is that these graphs show several days, but if we take a look at any of these graphs, in fact, at the concentration 0, which is basically the control, So, and which involves only cells, no nanowires. We see that basically the proliferation between day 3 in green and day 5 in purple, it's really not so different. And we believe that basically this indicates that cells have reached confluency, basically meaning that they have achieved maximum growth. So although it is here, we will not be discussing day 5 in purple. So let's get into work in what these graphs are showing us. So if we look at the chemical tellurium nanowires here at the top, image A, what we can see is that on day 1, it looks like biocompatible only at really small concentrations up to 10 micrograms per ml. But this basically completely changes on day 3, like it's starting to grow up again at 15 micrograms per ml. And basically what we see is this up and down, these irregularities, as we were saying before, might be related again to the morphology and shape of the particles, and basically might induce a different biocompatibility profile. On the contrary, though, when we observe the green tellurium nanowires on image B, what we can see is that concentrations up to 25, 50 for a 3-day analysis are somehow biocompatible. And the most significant differences, however, come when we treat melanoma cells, which are basically the 2 graphs at the bottom. So what we can see in graph C is that when we are treating chemical tellurium nanowires, only really high concentrations of 100 micrograms per ml are effective towards melanoma cells. However, even small concentrations of 15 micrograms per ml of the green tellurium nanowires in graph D already show this reduced proliferation. So basically, summarizing a little bit, is that green tellurium nanowires have enhanced anti-cancer and biocompatibility in comparison to the chemical tellurium nanowires. And this might be related also to the presence of organic coating surrounding the structure. Next, please. So to clearly see this cell interaction, do electron microscope images of the green tellurium nanowires, because those were the ones showing good properties. So here at the top, we can see basically HDF cells. So what we see is that the nanowires, which look like this kind of sticks, basically don't interact with the cells. They are basically surrounding it. The cells are growing on the top, on the bottom, but really not, there's no rupture that you can observe. However, when the nanowires were used towards melanoma cells, which are the images at the bottom, you can see these kind of bubbles in the first image that are pointing in orange. And there's also swelling of the membrane. And on the next image in blue, there's also observed some kind of rupture in the membrane. And this is commonly associated to a mechanism of cell death that's called apoptosis, and it's also known as cell programmed death. So we can see that melanoma cells are dying. Next. So finally, we wanted to investigate in more detail the possible antibacterial effects of these green tellurium nanowires. And for that, we use colony counting assays. So for these experiments and the rest that I will be talking about today of bacteria, we use 2 different bacterial strains, one being multi-drug resistant Escherichia coli or MDR E. coli, and the other being methicillin resistant Staphylococcus aureus or MRSA. And these 2 are the drug resistant strains that we were mentioning at the beginning of the most common type of bacteria that cause skin infections. So what we are seeing here in both cases is what it's called a dose-dependent inhibition of bacterial proliferation. And in both cases, starting between 10 and 15 micrograms per ml. And this dose-dependent inhibition basically means that the higher the concentration of green tellurium nanowires in this case, we see a higher decrease in bacterial concentration. So although the results are more clear in MDR E. coli than MRSA, the profile is completely exactly the same. And basically, green tellurium nanowires are useful for both bacterial, have anti-cancer effects for both bacteria. Next. So let's summarize our findings so far. And what we have seen is that the tellurium nanostructures are cytocompatible, have anti-cancer and antibacterial properties, and is especially true for the green tellurium nanowires. We have also came up with an alternative route of synthesis that is basically less hazardous than the traditional one. And finally, because of this such a unique structure that the green tellurium nanowires have, we believe that they should be studied in depth for further applications. Next. And that's basically where the second part of the project comes up. So the synthesis of, and this is the synthesis of tellurium nanocomposites. And again, this work is related to an article that's currently in progress and also a patent. So as I mentioned before, a nanocomposite is basically the union of two nanomaterials. And in this case, it's a metallic nanoparticle and the tellurium nanowire. So the synthesis process is as easy as it looks like. It's what it's called also an inside synthesis. So basically means that it happens in this moment and this time. And what we do is basically use the green tellurium nanowires that we have been talking about the last past minutes. And we mix them in aqueous solution with a secondary metal. In this case, we use either palladium or platinum. And after the purification process, we basically obtain the two nanocomposites. So it would be palladium nanoparticles growing on the top of tellurium nanowire, or platinum nanoparticles growing on top of the tellurium nanowire. Next. So let's take a closer look to the nanocomposites and basically try to understand how this process occurs. So here at the top on image A, we have the platinum nanocomposite. So these kind of sticks, again, are the tellurium nanowires, and then these spherical nanoparticles are made of platinum and are approximately 70 nanometers in diameter. And here at the bottom, we have the palladium nanocomposite, and again, the sticks would be the tellurium nanowire, while these cubes here are made of palladium and are also approximately 80 nanometers in width. So let's try to understand a little bit how these form. So if we take a look at the images on the middle, on the top one, what we see is in dark what would be the wire structure, and then in surrounding that structure in gray we have the starch. So that will be before synthesis. And what we believe it's happening is that when we add this secondary metallic salt, either the palladium or the platinum, these ions enter this structure. So they cross through the layer of starch and start nucleating inside the wire, but all surrounded with this starch, and start forming these nanoparticles inside the structure that we can see here at the bottom. This is, for example, the platinum nanocomposite. So this nucleation process that happens over time is what's called Oswald ripening. Next slide, please. So just as we did with the green tellurium nanowires, we also characterize the structure extensively, and here is a summary of the most important findings. So the first thing that we observed when we analyzed both nanocomposites via energy dispersive X-ray analysis or EDX is that in both cases we find either platinum or palladium, we coming from the nanoparticle. We found tellurium coming from the wire, and oxygen and carbon coming from the starch. And what's interesting though is that independently on where we look, we could find always more palladium than platinum, even though we use basically the same amount for the reaction. And we believe that these differences are basically associated to the differences in Radix potential. So if we look at the reactions here at the bottom right, we can see that basically palladium has a higher tendency to be reduced by the nanowires, and therefore more nanoparticles of palladium are formed. So that's why we have more palladium. Next. The other interesting thing that we found is that although I've been talking about palladium and platinum nanoparticles, they are in fact not pure platinum or palladium nanoparticles, but in fact they are palladium and platinum oxide nanoparticles. So this, for example, can be clearly seen here in the infrared, where we can detect at approximately 500 the bonds between palladium and platinum with the oxygen. Next. So if we evaluate these results closer, and we did that with X-ray diffraction, what we can see basically is that both structures are pretty crystalline. So if we take a look on the left, on the palladium nanocomposite, you can basically see that it can be related to palladium oxide pretty much. We can relate every peak. And however, when we do this for the platinum one, although it is displaced a little bit in between A and B, we can still relate the vast majority of the phases. However, there are some peaks that cannot be related, and for example, these are marked with this asterisk here, and this can be related with pure metallic platinum. Next slide. So what that information was telling us, it's basically that there is some platinum in the structure, and we could clarify this using XPS. And basically, in this case, what we can see is, for example, when we analyze the palladium nanocomposite here in B, is that for palladium, we have two compounds. We basically have the vast majority of palladium oxide, but we also have a small quantity of pure metallic palladium. But for the platinum here in green, we can only see pure platinum. So what this is suggesting in comparison to EDX and X-ray analysis is that basically the nanocomposite structure for palladium is probably made of palladium oxide completely. It might have some inclusions of pure palladium, but really not relevant. But the platinum one has a pretty unique structure, and it's formed by a pure platinum shell and a platinum oxide core. And we believe that these differences are because of the process of synthesis, because of this Oswald ripening, that the structures form in a different way. Next, please. So now that we understand a little bit the composition and how these nanocomposites look like, let's try to analyze the biomedical properties, starting with the antibacterial properties. So as we did before, we tested MDR, E. coli, and MRSA, and again, so we have here the results for MDR on A and B, results for MRSA in C and D. So in both cases, both bacteria and both nanocomposites, we still can see this dose-dependent inhibition profile, starting at small concentrations as 10 micrograms per ml. So basically what this is telling us is that both nanocomposites are antibacterial towards both bacterial strains. But if we take a closer look to the data, what we are seeing is that basically while the results for the palladium nanocomposite that are on the left side start at concentrations in between 10 to 15 this inhibition. For the platinum one, it already starts at really small concentrations in between 5 and 10. So the platinum nanocomposite is slightly more efficient than the palladium one, but again, in both cases are highly antibacterial with this dose inhibition profile. Next. So we also analyzed in this case the interaction of the nanocomposites with the bacterial cells, and we did that again by imaging them together with electron microscopy. So here at the top you have the images for MDR E. coli, and at the bottom you have them for MRSA. So what we can see is that when we introduce these nanocomposites, basically we focus on the images at the top in MDR E. coli, we can see this shrinkage and swelling of the membrane in comparison to the control. And it's even more clear with MRSA at the bottom, that basically the bacteria kind of splits and completely dead, is completely dead when we introduce the nanocomposites. Next. So the next step was testing cytocompatibility, and again we started using these metabolic assays. So again, as happened before, cell grows between day 3 and day 5, so in between green and purple. It's not really significant, so again we're not going to talk about day 5. And again, as a reminder, what we are looking for here is a decrease in metabolism, which is basically translated in a decrease of cell concentration and cell death. So in this case, what we are seeing is that when the nanocomposites were treated against healthy tissues, so in this case, both images on the left, is that both nanocomposites are still biocompatible up to concentrations of 25 micrograms per ml. The platinum nanocomposite is slightly more biocompatible. However, when we treated them towards melanoma, so the two graphs on the right, what we can see is that even small concentrations in between 5 and 10 for a 3-day assay are already producing this decrease in cell concentration, this cell death. So there is still a range where both nanocomposites show anti-cancer and antibacterial properties too, and are as well biocompatible. Next. So we decided to further investigate this anti-cancer activity basically on melanoma cells. So to explain this, I will be taking as a reference the platinum nanocomposite, but I'll show you later the results for the palladium one. You'll see it's the same story. And what we did then is basically use what's called a live data assay. And what this does is basically show if the cells are indeed live or dead after the treatment with nanocomposites. So this is because what we were looking with the MTS assay was this metabolism, and we made the assumption that metabolism is related to cell death, and we wanted to check if that was true. And that's in fact when we realized that the cells are not dead after a 24-hour treatment. So this is clear when we look at the images. So here at the top you have the results for several concentrations at 24 hours. So what we are seeing here in green are live cells, and in red are dead cells. So you can already tell that there are not a lot of dead cells here. Approximately only 20% of the cells were dead at really high concentrations, about 50 micrograms per ml to 100. So there is some dead cells are starting to die, but they are not actively dying. It's only like a damage process. However, the story completely changes at 72 hours. And as you can see, already at small concentrations like 20 micrograms per ml, there are already a good amount of red dots. There's approximately like 20%, and at higher concentrations, above 50 micrograms per ml, it grows up to 60 and 95% of cell death. So what this is telling us basically is that melanoma cells are getting damaged at 24 hours and are dying at approximately 72. Next. And again, the results are pretty similar for the palladium nanocomposite. It might be even more evident that cells are only getting damaged at 24 hours. As you can see, there's tons of green showing here, so tons of live cells. However, at 72 hours, again, same story. Cells are starting to die, and the higher the concentration, more dead. Next. So the next experiment that we did was, okay, we know now the cells are dead, but how are they dying? So it's basically trying to understand the exact mechanism of cell death. And as I mentioned before, cells can die through multiple type of mechanisms, such as like necrosis or apoptosis. And to start imaging this, we did again electron microscopy. So at the top you have image for HDF cells, and again something similar that when we saw with the green tellurium nanowires, we can observe here too. So again, we find these nanocomposites that are growing on the top, on the bottom. Again, not much of an interaction to cause disruption. However, when we test the melanoma, that are the images at the bottom, you can already see this kind of bubbles and swelling that's showing on orange on the right, and even completely disruption of the cell that we can see in image E. And this is pointing to a mechanism of apoptosis, this cell programmed death. Next. But to further investigate such mechanism, what we did was quantify caspases, or a caspase assay. And this is because caspases are basically enzymes that are responsible of starting the process of apoptosis. So basically, if caspases are active, which would shown here in green, would basically mean that the apoptosis process is ongoing and therefore cells are dying. So I will explain this taking as a reference the palladium nanocomposite, but I'll show you later the image for the platinum, and again it's just a similar story. So in a 24-hour assay, what we can see is that there's some active caspase. We can see some green dots at higher concentrations in between 50 and 100, and but there are not really a lot of green caspase, and this is probably associated basically because, as we saw before, cells were not really dead, so there's not a lot of active caspase because cells are not dying. However, at 72 hours, the story is completely changed, and basically what you can see is that at small concentrations in between 20 and 50, there's tons and tons of active caspase here in green, and this starts to increase in between 20 and 50, and then starts decreasing again. And although this makes sense, because as we were seeing before, basically what is happening is that cells are starting to die, but at higher the concentration it is, cells are already dead. So there's not going to be active caspase, is basically cells are already dead. However, the whole summary of this is that melanoma cells are showing this active caspase, therefore they are dying through apoptosis. Next. So here is basically an overlap in between caspase and live data say for 72 hours on the palladium nanocomposite. So you can clearly see what I was talking about. So just as a reminder, the top images are active caspase. So basically here, green means active, means dead. However, at the bottom are the live data set, live dead assay. So green means live, red means dead. So as you can see, at really small concentrations, we have these active cells dying, so lots of active caspase, and while cell death is increasing, we still have this active caspase up to concentration of 50, and then it starts to decrease because cells are completely dead. Next. So a similar pattern was observed for platinum nanocomposite, and when caspase, basically caspase starts to activate at 24, but I think here is even more evident that there's not a lot of active caspase, there's not a lot of active death ongoing. However, the story again changes at 72 hours, increasing at up to 50, and then starting to decrease again because cells are already dead. Next. And here again we have the overlap, but again it's showing us the same story. Basically, what we can see is that melanoma cells are dying through apoptosis in both kind of nanocomposites. Next. So the last step in this research was basically try to understand the mechanism of action of these nanocomposites, and that basically means we know that the cells are dying and they are dying through apoptosis, but how the nanocomposites are killing these cells. And there are different mechanisms of cell death associated to nanoparticles and nanomaterials. So one of the most accepted ones or more reported ones is what's called the accumulation of reactive oxygen species, or ROS. And another one is metal ion release. So let's start with ROS. So ROS are basically species of oxygen like peroxides that are normally generated in metabolic processes. However, if there's an imbalance produced because of the presence of these nanomaterials, they can basically accumulate inside the cells and rise the levels of oxidative stress in the cellular environment, and basically induce cellular damage, which can cause cellular death. On the other hand, because the nanocomposites are made with metallic particle and metalloid wire, it is possible that these nanostructures are releasing ions to the media. And basically, these ions can interact with the cells, they can accumulate inside the cells, and basically trigger cell death. Next. So what we did first was to measure and quantify basically these ROS in a period of 24 to 72 hours in both nanocomposites. So what we can observe here is that some concentrations in both nanocomposites, like 30 or 40, produce an increase of reactive oxygen species, an increase in fluorescence. And this is true in between periods of 24 and 72 hours. But also some concentrations like 90 and 100 produce a decrease in this fluorescence, in also true in between 24 and 72 hours. So basically, some concentrations increase, some concentrations decrease. This shouldn't be much of a problem because both an increase or a decrease in reactive oxygen species could still cause this imbalance and cause cell death. However, as you can tell, there's basically no apparent pattern. So just some concentrations increase, just others decrease. So it is possible that ROS are contributing to cell death, but it's clear not the main mechanism. Next. So as last research, the last step was to quantify basically this metal ion release. And for that, what we did was atomic absorption spectroscopy. And what what this does basically is measure the amount of, in this case, tellurium, palladium, or platinum ions that basically were accumulated inside the cells. And what we observe here is a clear dose-dependent metal ion release over a 3-day experiment. So here what we can see in both cases for the palladium nanocomposite in the left, the platinum nanocomposite on the right, is even small concentrations of 10 micrograms per ml of either nanocomposite already shows significant metal ion release. Basically, you can also see that the amounts of palladium or platinum are increased within time of exposure. So, for example, if we take a look on graph A, palladium that's shown in gray, it's less than, which is 24 hours. It's less than palladium shown in blue, which is basically 72 hours. So the higher the concentration of nanocomposite we use, more ion release, but also the more time of exposure, more ion release. So the other interesting thing that we observed is that more palladium ions were detected than platinum ones, even though, again, we use the same amount. But this is related to what we were discussing at the beginning, that basically more palladium nanoparticles were formed. So basically, we expect more ions to be released. The other important thing we observed is that in both cases, we still can detect tellurium ions, and in a dose-dependent manner too. And basically what this is telling us is that not only palladium and platinum are contributing to this ion release, but also the tellurium. So every part of this nanocomposite is participating in this ion release. So every part of this nanocomposite matters. And the last thing I wanted to mention is that basically, as we were mentioning all over, is that although we have used similar amount, we have more of materials, we have more palladium nanocomposite, and the results, the biomedical performance basically in between these two materials is slightly similar, but slightly better for the platinum one, and we have less amount of the platinum nanocomposite. So in those way, the platinum nanocomposite is slightly superior than the palladium one. Next. So let's try to summarize what we have seen so far in this section, and it's basically that we have created an in situ reaction capable of producing nanocomposites without the need of any extra reducing or caping agent, and basically reusing the previous green tellurium nanowires. We have also proven that the nanocomposites have antibacterial, anti-cancer properties, and are also biocompatible with high efficiency, higher efficiency than the plant nanowires. We have also seen that, in fact, what's happening is that the nanocomposite induce metabolic damage during the first 24 hours, and then cause cell death around 72 hours, and then the cells are dying, in fact, through a process of apoptosis. And finally, that the probable mechanism of action is mainly associated with metal ion release. And although it's possible that ROS is also involved up to a certain degree. Next. So let's summarize the global conclusions of this project and try to match those with the objective we were talking at the beginning. So basically, we have found less hazardous route of synthesis of tellurium nanowires and proven that tellurium can be used for biomedical applications in the skin. We have reused the green tellurium nanowires to create nanocomposites and showing basically enhanced biomedical performance. And we have proven that these nanocomposites, again, can be used for biomedical applications on the skin. And we have also understood the mechanism of actions of such materials, and now we could use that to better engineer them for the future. Next. And finally, I wanted to talk a little bit about what the future work or opportunities of this project might lead to. And as I was commenting during the talk, basically two different patents were filed in regards of this project. So it is believed that this tellurium material could be used for real medical applications, like thermal patches or coating of surfaces like orthopedic implants or other medical devices. And this is in fact what is already under investigation in different startup companies, like the one shown here at the bottom, Cell Biotechnology and Nanolix. And the only thing I wanted to mention, though, is that there is still plenty of room of investigation that basically needs to be done to use these materials in vivo. For example, resistance studies, dosage aggregation profiles. That basically it's just investigating more in depth the antibacterial and biocompatibility properties. Next. And last but not least, I basically wanted to thank everyone that helped me along the way. So these are my lab members at Northeastern University, but also all my international collaborators, well, national collaborators like the University of Arkansas, as well as the international ones in the Tecnológico de Monterrey in Mexico, and also here in Instituto de Micro y Nanotecnología in Madrid. And thank you everyone for being here and listening to me, and I would be really glad to take any questions. Thanks.
So thank you very much, Ada, for this presentation. As there are about 20 or 30 seconds delay between the streaming in YouTube and this platform, I am going to start asking you what are you going to do now once you have finished your PhD? So please, can you tell us about your future?
Absolutely. So I'm going to start now working on a company doing cancer research, and so I'll be actually starting in a couple of weeks. I'm really excited about that. So I think that in the States actually it's more common maybe than in Spain, but it's really common to jump from academia to industry. There's a lot of opportunities. And I'm jumping on this company that it's a little bit bigger than a startup, but it's basically still on the research part. So it is just getting a little bit more into a translation of how the research that we actually do in universities or institutions can basically be translated into actual work for patients. So that's basically what I'll be doing.
Okay, thank you. Can you comment a little bit about the difference between palladium and platinum? Because okay, you said that platinum was working a little bit better than palladium, but of course the price of platinum is much higher. So do you think that it is worth such a difference, or that with the palladium would be enough?
That's a really good question, and that exactly depends on your money. So as a science part, as we've been seeing in the talk, right? So because we will need less amount of platinum, it works better. Therefore, I would say yes, it's worth it because it does perform better. It's more biocompatible and has more anti-cancer and antibacterial properties. However, in terms of economy, that is completely true. The difference in between palladium and platinum, it's that palladium is approximately half the price of platinum. So the results are slightly similar. So both nanocomposites would probably work. And therefore, if you need to bring this to the market, then I would say, yes, you should go with the palladium nanocomposite, because the money that unfortunately does matter all the time. So you could make a more profitable nanomaterial, and you could probably sell it for better, and the environmental impact and everything, it's quite similar. So I would say go with the palladium one.
Okay. As you have experience with several patent applications, I would like to ask you if you have started the process of getting approved by the FDA in the United States for medical application of these nanomaterials.
So as I mentioned in the talk, the patents that are involved in this project are taken by 2 different companies. So the answer is a little bit complicated. Okay, so if you want to put this inside the body, I'm not really sure in Spain, but the FDA in the States is makes this process really complicated. So once you want to put something inside the body, it will need to go inside clinical trials. It will need to have different phases, try to see if it's working or not. So it's basically going to delay the application of this several years. It could go up to like 25 years. Like it's incredibly insane the amount of time that it would be put into this research, which I mean, it makes sense again, because it needs to be inside the body, so it needs to be safe. But I'm saying this because the approach that we are taking with these nanocomposites, along with other materials that we have patent to, is to use them as coating of surfaces. And although it's not the same approach, because you are losing some of these wonderful properties like the anti-cancer or biocompatibility ones, but still they are pretty useful for bacterial growth. And when you are using these for coating of medical devices or surfaces that don't need to be in contact with the body, the process is really straightforward. And I'm pretty sure it doesn't even need like in vivo studies, because it won't be in contact with the body. So that basically means that in a couple of years, if you have the infrastructure and if you have the money, this product can go to the market. And for example, this was starting to be commercialized, not our product, but some similar ones, and using nanotechnology. For example, when COVID started, if we want to say that, a couple of years ago, they started to use these kind of like papers that were putting on the doors, and they had different, I think they were silver nanoparticles. Now I can't recall, but that was all. Like that was really approved for like an emergency use, and I think it was only like 1 year of investigation. And this is an example of like how easy, how quick, and how profitable can these technologies be used if they are for external use in the FDA, at least.
Okay, so I think there are no more questions. So I would like to thank you for your availability and for waking up early today.
It was hard. But yeah, thank you for inviting me here, and it's really a pleasure to be talking in Spain, it's my country, it's where I grew up and where I studied, so it's really wonderful to come back.
Okay, thank you, Ada, and good luck for the future. We'll be in touch for sure. Bye-bye.
Thanks, bye.